several of the developers of them are in this room right now. And these are great. However, the thing about the proof systems is that they're kind of specialized in the world where you have a complete axiomatization. So in classical quantum mechanics, for example, you have a complete axiomatization and you can do everything inside this synthetic world of string diagrams. So everything you care about can be completely described by string diagrams. However, there are also parts of applied category theory where we would like to use string diagrams as a tool for describing morphisms in a category, but we don't have a complete axiomatization. So we're just using this as a tool, as part of our toolbox, but not the complete thing. Next slide, please. Okay, so here's some examples. So you might want to use string diagrams to specify programs in a programming language. So that's what they're doing with statebox. In complex systems, so what John Byers and his group are doing, for example, and Pavel and his collaborators are doing, you want to describe complex systems which don't necessarily have a complete axiomatization. It's very nice when they do, but they don't always. DiscoCat is a very interesting borderline example. We got into a discussion in this after Colin's talk yesterday, because technically it does have a complete proof system. It lives in real vector spaces. But in practice, you push the dimensions of your matrices as high as you possibly can until you run into the limits of NumPy sparse matrix library. And so there's this question, and my default assumption, I'm willing to be proved wrong, but my default assumption is that double push-out graph rewriting is never going to outperform MATLAB sparse matrix library in a million years. I'm willing to be proved wrong on that. Game theory is another example where, so we haven't had any computational game theory talks, but in open games, you pretty much have to use string diagrams to describe your morphisms. So they're just too complicated to describe any other way. But you don't have anything remotely close to a complete proof system, so you still have to work out what the morphism is and then calculate it. The category of open learners we saw several talks about is another example where you can draw string diagrams for these things, but that's just a description. You can't run the semantics of the learning and stuff inside the string diagram. It doesn't describe that. So we're using string diagrams as a specification language. So what we would like is a compiler where the user can draw string diagrams on the screen with some graphical interface and then push a button. And then what it does is it decomposes the string diagram by making cuts, vertical and horizontal cuts, and that then describes a morphism in the logical language of the modal categories, right? You have terms in the language of morphisms, you have a tensor operator and a sequential composition operator, right? And then from there, you can then send that to various different domain-specific backends. So for example, you can take this term described in some standard representation language like JSON in a computer, and then you can compile from there to MATLAB or to Python, or might as well go to the next slide because I've already started on it. Okay. So this is what I'm describing now. So here's the kind of obvious architecture for this thing that several people have thought of independently. So we have a front end which is some graphical editor, and we're probably going to have several different rival versions because different people have different ideas of what is nice to use. And there's also some very considerable trade-offs in design of this thing. And then we have this kind of intermediate language, which is just the logical language of the modal categories implemented in something like JSON. And then you can compile from there into whatever target language you like that's specific to your problem domain. So for complex systems, you probably want to go to Simulink, right? You're not really going to do serious work in complex systems without Simulink. For open games, I have a library in Haskell, so I want to compile to Haskell code for that. Yes, okay. So what's the string diagram? Okay, I'm going to go through these slides very quickly, so I'll stand over here. Yeah. So what's actually string diagrams? So you look at this thing and you chase the literature, and then you go back to Jelle and Street's 1991 geometry and tensor calculus, and you find that string diagrams are actually defined in terms of things called topological graphs, which is something like a graph together with a smooth immersion in the plane, and some singular points for the nodes. So the nodes are actually point-like. This box notation that we use is technically an abusive notation. Technically, nobody's proved it's correct, but of course it's correct. But technically, they're point-like. And you can look in something like Hatcher and find that this is the same thing as simplicial 1 complexes. Okay, so what else could they be? Well, okay, an obvious answer is graphs. Okay, so the obvious representation of string diagrams in a computer is definitely graphs. And I'm pretty sure quantumatic and physics use this. That could be wrong. Someone's nodding. Okay. Okay. And it's quite nice. You can get different flavors of categories very easily. So general graphs give you CCCs. Directed graphs will give you non-self dual CCCs. DAGs will give you symmetric model categories. Planar graphs. Okay. So planar graphs are a bit of a headache, right? So detecting planarity of a graph is kind of annoying. You can do it. It's not inefficient. It's just not really obvious. You got to do some work and read some graph theory papers. No one wants to do that. Why would you care? There's two reasons you might care about planarity. One is that you have an application domain that's a non-symmetric model category, of which basically discocatas, grammar categories and discocat are the only big example of that.
I like categories.
Yes. Okay. Thank you.
That's a large class.
Yeah. Okay. I'm talking about for applications where you have some backend that you might want to apply.
Category theory example.
Okay. Category theory is a backend. But the other reason is that we might want to control where the symmetries go. We might not want to hand that over to the computer. We might want to give the user explicit control over swaps. Planar graphs are a bit of a headache. There's actually some recent papers on dynamic editing of planar graphs. So there is literature on this. This is a solvable problem. It's just you've got to read some fairly technical graph theory papers. Rotation systems, which Marlon talked about on Wednesday, might be a very nice representation for general purpose use. So this is a less obvious representation of planar graphs. So it's a representation which is not the same as a graph with an invariant that says it happens to be planar. It's a different representation. I think I've been thinking about a lot recently is something that I think is probably the Poincare dual of that, maybe, which is polygonal subcomplexes, where you store the faces, and then so if you remember for a rotation system, you remember the nodes and then the ordering of edges around the nodes. But in this, you're going to store the faces and the ordering of edges around the faces. So I've been head scratching a lot about the combinatorics of these things recently. Okay, changing direction. Why do we actually care about string diagrams? Okay, so the basic result of string diagrams is the Jelle-Street theorem in geometry extensive calculus 1, which says that if you have a monoidal signature, then the free monoidal category on the monoidal signature is equivalently the category of string diagrams modulo isotopy. So it's a concrete geometric description of the free monoidal category that's defined by universal property of freeness. And the universal property of freeness is the thing that you actually use every single day, that says that if you interpret each bit of your string diagram in a category, then that uniquely defines a morphism. You can just stick them together in the obvious way, right? So the Jelle-Street coherence theorem says that this doesn't go wrong. And this is completely blindingly obvious, to the point where people just do this instinctively, like having never heard of this paper that proves it, or knowing or even thinking that they're using universal property, right? It's just obvious. Sorry, coughing in the microphone. There are other descriptions of free categories other than the geometric ones. So there's another general family of descriptions of free categories by Hambeck, which says that morphisms in free categories are proof trees modulo things called commuting conversions, which are equivalences on proof trees. And I haven't found a specific proof for monoidal categories, but it's kind of obvious folklore, whatever, is that this is a non-commutative linear logic of tensor. So the category of proof trees of linear logic of tensor modulo commuting conversions is the free monoidal category, and the category of string diagrams modulo isotopy is also the free monoidal category, so they're equivalent. So we should be able to pass between proof trees in linear logic and string diagrams. And in the middle of this equivalence, I introduced this thing called KD trees. So KD trees is a base structure from computer graphics which recursively partitions a space by hyperplanes. and this is used for various applications in computational geometry and computational geometry and computer graphics. An example of a problem that this is used for is nearest neighbour finding for clusters of points in a high-dimensional space. So I just I put KD tree in Google Images, and a bunch of examples came up, so you can just see what this thing looks like. Okay, you got. So this is KD trees in 2 dimensions. So you recursively partition. So there's a general class of structures called binary space partition trees, and then KD trees is the special case where all of your cuts are aligned to the coordinate axes. So you've got vertical cuts and horizontal cuts. Okay, so sorry. K being 2. Okay, so the official. So originally KD meant K-dimensional, but nowadays the terminology is a KD tree of dimension 2, because terminology is weird everywhere. Okay, so bigger examples. There's a really big example. This is just on the first page of Google Images.
What's the date of those examples? Are those the spots in the?
Sorry?
What's the data? What's the algorithm? What's going into the algorithm? What's coming out of it?
No idea.
Points are going in. So like the dots are the coordinates, and what comes out is this tree of cuts. So at each node you have either horizontal or vertical cut, and it's just branches like on the left side of the cut and the right side. And every time it alternates horizontal and vertical.
So would it be fair to say that these describe a way of partitioning?
Yes. Yes. Of course, they're highly non-unique. This is a completely stupid thing that came into my head, is that, well, people care about rebalancing these trees, partitioning in different ways for efficiency reasons, and I reckon that this should be basically the same as strict and categories. So I reckon that if you look at the definition of a strict and category, it's computational geometry people worked this out decades ago. That's my crazy idea. Okay, I should speed up through the last part. Okay, so if the strict monoid category is the same thing as a one object 2 category, then you can draw pasting diagrams, and actually this is the same example as this one. Okay, so this is now a kind of running example. If you draw it as a pasting diagram, you get this. And of course, obviously, this is a simple example, so it was easy to do. But these are completely impractical to do for any series work. So there's a medium-sized string diagram there, and you wouldn't want to draw that as a pasting diagram. On the other hand, if you pretend that your strict monoid category is a double category with one object and one horizontal, one cell, you get these cubical pasting diagrams, and these are much more practical to actually draw on a page. Right? This is a completely non-technical distinction. This is just these are more practical to actually draw. And you can fiddle around with these. If you take an extra concrete, you'll adjust the vertical edges, then you get something fairly nice with the brick diagram, which basically Jelle independently invented. And I realised that this is cubical pasting diagrams. Sounds terrible. The Psycho logo is one of these things. Assuming that the empty space is an identity. And these things also study combinatorically. So there's a couple of papers on these things called tile orders, and they're related to double categories, of course. So in conclusion, these things are basically pretty much the same, more or less morally, give or take some details. That's the conclusion. And then the idea is, okay, you could do some hard theory with that, but hard theory is hard, let's make a tool instead. So over to Jelle. So Jelle actually made this tool. I had nothing to do with programming.
So actually sure did the other thing.
Okay.
Okay, can you do this?
Yes, nice. Okay.
Okay, so I have 10 minutes or something? A little bit less? 7?
Sorry, I overran.
That's fine.
You have 10 minutes.
10 minutes? Okay.
Okay, so.
Yeah, so I thought it would be worthwhile to share for a second the background, like where this came from. So I think this is in 2000, well, December 2000, a demo crew released this thing. This is a 64 kilobyte piece of code. I'm just going to show you very quickly what this looks like. This is of course on YouTube because this thing runs on Windows, so it's a bit hard to see. But I'm just going to skip through it a little bit. So this generates audio and synthesis and all that stuff from basically a small email. You know, it's like your average email can be bigger than this thing. I spent a lot, as a kid, I spent a lot of time trying to code up these things. You can see it just goes on and on. It's basically a small movie from a tiny amount of bytes. And it was extremely fascinating to me how they did this. And the way they've done it is using this tool called Werkzeug. It's from a crew called Farbrowse. And here you see what essentially led to like this big brick diagram thing. So there's a flow from top to bottom. Torus goes into projection, goes into transform, it's stored. Like, I'm not going to explain like how this tool works, but this is to do 3D scenes. And kind of maybe I started, oh, I can probably use this for other stuff as well, so I tried to build it. Here is our recent version of like an attempt to rebuild this tool, and it's essentially drawing these string diagrams without the wires, because the wires is the thing that makes the visual programming super annoying, because you need to, with your mouse, fiddly draw the wire from the port and do the arrangement, and that's why text is better. So here I can actually show you, this is the tool, and it doesn't really like that I make my browser big. So this is another attempt. I can just drop these nodes in here and like drag them around and maybe make another node, and now I've somehow connected these two things. And so you can, yeah, this is just a way to quickly build up your diagrams. Here is the same thing, but this is the tool that Jules just mentioned. This is an implementation of this theory. And the way you should think of this is that I have now a 1x1 image here. This is called the pixels, or a friend of ours, Radek, suggested brixels. By the way, the name from brick diagrams was suggested by Fabrizio. It's also worth mentioning. I think it's a great name. So I have a 1x1 image with one pixel with the color F, and here in my context I have this signature for F, so it's from A to A. If I add a second type to my signature, you get something from A to B. Now I can add another function, let's say G, which goes from A to B to C. And then I compose it like this. So the tool figures out how to draw the wires for you. And again, you see these are these two bricks. And if I press Alt, it disappears, and you actually work in. So we're going to combine, of course, these two tools. You're not going to enter your pixels, but you will really be working in this setting with full keyboard control. If I instead put the thing below, I get the tensor. So in this case, the flow is from this side to this side. Of course, we're going to make that in whatever orientation you want, because we don't want to do these holy ones.
Yeah, this is the correct orientation.
Yeah. What you also notice in the bottom is this term view. So it's a little bit here. So you see in the corner, you see the product. And if I move my cursor, it highlights which term I'm looking at. So I can make them bigger. So now I have FF, and I put, for instance, an identity here. So you see how the term view changes, right? I have now the identity here, I have a G here, and I have the F here. And if I select two things, here over here, you see there's a little type checker under the hood, which constantly computes the type of this thing. I could put another identity here, so you get this thing, and if I change the type of this one, it will propagate along the wires, etc. And this is, I mean, yeah, this is it, in a sense. I can show you some more complicated diagrams. So this is something more complicated. Press Alt. So you see that it has no issue laying out these wires and computing the types again. The selection, it automatically enlarges to whatever block you have under it. You can select two things. You see how it keeps checking this thing. We can also do holes. So we can do yeah, you just have an unfilled, and this is not yet implemented, but shouldn't take too long. So if there's an empty space, we can figure out what shapes fit in this space. There's no explicit things like a swap, but we have or copying, for instance. So here we just add the copying thing to the context. We make it a bit smaller. So here you see delta is a function from. Is a box with signature H to twice A, so that's this thing. And here we do swaps. So this X node, this big X node, is here it's permuting the 2 and the 3. So if I change this, you get this diagram, right? And if I do 4, 3, I mean, it does what you expect it to do. And then I guess the other thing I should show, here's another diagram. I mean, I could show you hundreds. And another thing I should show is that if you go to the console, so we export this, we have this representation of the term you see in the lower bottom. And this is just standard JSON. So here I've pasted it inside this tool that formats it nicely. And this is the thing that you feed to your compiler or interpreter or graph rewriting system or simplification system or whatever it is. This is just an exchange format. It could be JSON, it could be XML, it could be something binary. We're probably going to use our own system called typedefs to do these things, but yeah, that's more or less it.